this talk is somehow, a very good backdrop for my talk was given by Stefan earlier this morning, and also somewhat, in that sense, it was given by John yesterday. And so what I'm going to talk about is not necessarily entirely linked to multiscale statistics of the kind that Stefan mentioned this morning, but there's definitely one instance of what we're trying to do. So basically, the talk will be about trying to use these new representations provided by either the scattering transform or potentially convolutional neural networks or what have you, any representation in actually regularizing inverse problems. And so the setting is very standard. We want to solve inverse problems. We always want to solve inverse problems. There's some forward operator gamma, and we get some data measurements y that are corrupted by some noise. The kind of inverse problems that we want to solve in my talk will be linear inverse problems, and I'll take gamma to be such that the inverse problems are real posed, meaning that if you perturb your data slightly, this can correspond to wildly different parameters that they have caused your measurements. And two examples that will be running examples through the talk, or at least cartoonish versions. By the way, this talk will be largely speculative, and I like to call it the cartoon version of what we do, which would maybe make you think that there's also a non-cartoon version, which is not true. There's only a cartoon version. But yeah, it's life. So you're here, you have to listen to it. Yeah, so first one is super resolution, and everyone knows super resolution, or deblurring perhaps. The thing is that you measure a part of the spectrum, a lopez part, and you want to find high frequencies, but you only know low frequencies. Another one is tomography or radon transform, where you only know the spectrum along some radial lines, and both problems can be summarized as knowing some part of the spectrum and trying to learn or infer what the rest of the spectrum is. Okay, and because this is a conference on data science plus inverse problems, then I thought that I'd give just a very sweeping overview of what people have been doing in applying learning to inverse problems, but I will not go too much into it because Mike McCann will give a probably much more detailed version. The way we solve inverse problems is typically by minimizing some energy functional, and you add some regularizer to it. So everyone knows about it. I will not talk too much about it. Then people started kind of adapting this regularizer. This regularizer can be something like L1 or TV norm, which promotes certain forms of sparsity, or it can be something more sophisticated. Then what people started to do, maybe in the 2000s was, or even earlier, is to stick, either a wavelet transform or a dictionary or something there, and saying, well, I actually want my signal to be sparse in a certain transform domain. Another version of that is something that's called synthesis sparsity, where you say, I want my signal to be sparsely created from a few atoms in a dictionary. Okay. So that was like the first, because those dictionaries can be learned, you can call this machine learning for solving inverse problems. With the advent of convolutional networks, much more complicated, sophisticated stuff became possible. And so one example that was mentioned yesterday by Carola Schönlieb, who, by the way, when she started her talk, I was certain that she's going to give this talk and that I could just close the shop. So I'm happy that she didn't, but yeah, I mean, so you can do monster things. So one example of things that you can do is you have iterative schemes for minimizing those loss functionals, like gradient descent, for example, different first-order schemes. And now the game in the last couple of years is to try to learn updates in these iterative schemes. So for example, instead of computing the gradient in your gradient descent based on the actual loss that you have, you just use some loss, okay, as an input. Well, the gradient of some loss that's analytic as an input to a huge neural network that, in addition to this loss, maybe takes also the gradients of the loss in previous time steps. Maybe it also takes some extra information. It takes a ton of stuff and then produces the optimal update that takes you the fastest possible way to your solution. This clearly requires a ton of training data, and it's very complicated, very hard to analyze. And then there are what I call correction approaches. And again, I don't want to dwell on this too much, but these approaches are basically, you solve your inverse problem using some method. You get something that's, like a rough version, not a great version of what you want to get, and then you use a neural network to kind of correct it, to just, do the delta and, for example, improve resolution. Okay. And then maybe you have something that's called full-on learning, and then that's where the input is actually, for example, the sinogram, your data, something that's in the transform domain, in the space of your operator. And this is the hardest version, and maybe certain unrolling approaches could fit into this category. but perhaps it's just a subset of the previous one. As I said, Mike McCann will talk this afternoon about this in much more depth. In fact, IEEE Signal Processing Magazine had 2 issues in November and January on something called deep learning for visual understanding. But in both these issues, there's one article on applying learning for inverse problems, applying convolutional networks for inverse problems. And it's a very good overview. There's tons of papers that they mention, and you should probably read it if you're interested in the topic. Anyway, so there's 2 ways I think, or someone can think about regularization. So one way is, you need to deal with ill-posedness. You want to bring in some prior information as a designer to your inverse problem. And you can see this prior information as specifying a bunch of properties. You could say, my properties will be some functionals on X. And, maybe, I want the property 1 to be like that and the property to be like that. This is typically cast as minimization of a certain energy functional. But I'd like to concentrate on this kind of property, specifying property viewpoint a little more. And to explain to you what I mean by properties, I'll give you an example. So suppose that you have a data set of images, for example, brain slices, and you're trying to solve an inverse problem, which is, for example, deblurring. So what the data that you get, what you can measure, is a bunch of blurred brain slices. And now your task is to recover the high frequencies. Now, the way you formulate this inverse problem is to say, well, find me something that's consistent with the blurred version, but it also optimizes a certain criterion, a certain property that I know is true about my signals. And so you can just come up with some ad hoc property. In fact, I'll first give an example of an L1 norm, which is a bad idea in this case, but just for the sake of an example. So let's say, we're trying to minimize or specify an L1 norm of images in the top row, having only images in the bottom row. So first, what we can do is we can compute a histogram of L1 norms of the sharp images, and it's something like that. So already you can see that, it's not a completely random, it's not a random number. So it cannot be anywhere. If you say that it's 7,000 plus minus 1,000, 1,500, you'll give a very good guess. And the second thing that you can do is you can say, well, maybe my data Y actually tells me something about the L1 norm of the sharp image. So let me try to regress the L1 norm of the sharp image on the basis of Y. And for example, I can use the L1 norm of the blurred version to regress it. And so what I'll plot now is the histogram of the residual shifted by the mean so that you can compare it. It looks like that. So it's perfectly regressed, which of course is laughable and says that the L1 norm is wrong in this case. It's just because the image is positive and the filter is positive. So the convolution has the same L1 norm as the input. Maybe something more sophisticated that's actually more appropriate for this problem would be more interesting, and that's, for example, the total variation norm. Again, the histogram of total variation norms is something like that. So, always in these schemes, you have to set the lambda, the regularization parameter, and if you just plot this histogram, you had a very good idea of what this lambda should be. But if you just say the TV norm should not be too far away from maybe 20, you'll be doing a good job. And again, you can try to do something similar. You can try to regress the TV norm of the sharp image on the basis of your measurements. Now it's going to be much harder, but I can, for example, take the L1 norm and the L2 norm of the blurred image and do a linear regressor. This is what I get. I reduce the variance by about a third. It's not great, but maybe if I use more sophisticated regressors and more features, maybe I can reduce it further. Okay, so you can reduce the uncertainty about properties, which is not surprising, about some properties of your sharp image from the blurred image. Okay, this really motivates I just cut to the chase. So this really motivates the kind of regressor, the kind of estimator for solutions of inverse problems that I'll talk about in the rest of the talk. And that's something that we can call moment matching or feature matching. So you have a certain set of properties, moments, generalized moments, which is specified as a vector of moments phi, and you have an estimator that you compute from certain class of estimators that we can call theta, and it's supposed to guess this phi, this moment vector phi, from the observed data. And then you want these things to be close in a certain metric. And it's really expressing in a very naive way the idea that, if you know certain properties, certain desired properties of your class of signals, then you should actually enforce them. And this is a completely ad hoc way, and we'll see that it can actually be motivated in a little more principled manner. Okay, so again, like a cartoonish way that I like to think about is you could write out a constrained version of the thing above. You could say, well, my data Y tells me that anything reasonable should be localized within this feasible set, which is basically a preimage of the noise ball around the data y. Okay, so anything reasonable should fall within this set. And let's say that the true solution that you're searching for is given by this star. And the role of those features is to somehow help you localize the star. And you could say, well, the first feature of y1, it gives you a cutout of this set. Of course, it's not convex because the whole thing is not convex. And by the way, this is the last time I say it, I will not care too much about it. Part of the reason why I will not talk too much about it is that, for example, John, yesterday in his talk, explained that in some sense, if your parameter space is large enough, then there are good reasons to believe that you don't have to worry too much about this non-convexity. Certainly, if there is just a single feature, you'll have to worry about it. But if the number of features grows large, then maybe there are certain effects that let us kind of just forget about it. Okay, and so the second feature maybe gives you a little more localization, and the third feature maybe gives you more localization. And if you do things right, so if you don't, if you set this Q, the metric right, and lambda right, then there is some hope that, well, eventually localize the right solution. Now, there are two obvious questions. The first question is, does this model anything we know? So common ways of regularizing inverse problems, do they fall into this framework, or this is just something completely different? And the second question is there a principled way of deriving this? Not just saying, well, there's a bunch of moments, there's a bunch of estimators, let me try to match them. To answer the first question, we can look at the, at the kind of the standard norm, bounded norm regularization. Okay? And in this case, we just take the feature of our, that we want to match, or the moment that we want to match, to be some norm. I'll take the TV norm, it doesn't matter, just letters, right? And the usual estimator in this case is, well, kind of the penalized version is you add this norm and you multiply it by some h, which is the multiplier that you have to determine somehow optimally for your data set. Okay. Now, when you think about this second one, the convex version, you can also write it in the constraint form. And now, if you get the solution, x star, that does not saturate the constraint, then in some sense, x star is also an unconstrained local minimum. So it's unconstrained global minimum because the thing is convex. And so it's maybe not the interesting case because you're not really regularizing. Okay? So the more interesting case, in some sense, is when you saturate the constraint, meaning you're actually regularizing something. You're doing something. Okay? But if you saturate the constraint, meaning that S equals xTV, then you can write it in this funny way. You can say, well, the difference squared of S and TV is 0. And I can again, convert this into a Lagrangian form from some lambda star. This has precisely the form of our estimator, if you set S to be equal to theta of y. So in some sense, in some cases, it's in the, this is, norm minimization is a special case of our framework, locally speaking. Okay. Now, the second question is perhaps, more interesting because this may have been obvious to some, maybe not, I don't know. The second question is there a principled way to derive such estimators? And now, because I'm really, I'm new to this inverse problems game, the only principled way I know of is maximum a posteriori. Well, I'm joking, I know of like maybe two more or one. But, map estimation is a really good way. It's well understood. It's not necessarily like the best thing to do. Oftentimes it's not, but it's principle. And so let's try to see whether we can fit our stuff within the map framework. That will be tough at the beginning. So for those of you, like for those two of you who don't know what maxima posteriori is, you assume that your data is generated, is random. Okay? It's generated from some distribution. And your measurement system, your observation is characterized by some, by some distribution, conditional distribution of y given x. That characterizes your gamma and also characterizes your noise model. And it turns out that what you really want to compute is the posterior. So once you see your measurements, you want to know what the reasonable distribution over the actual parameters, the signal that you're trying to reconstruct is. So one way to extract a point estimate out of this posterior is to take the mode, to maximize it. As probably everyone here knows. The trick there is that this posterior is proportional to this noise model multiplied by the prior, and this prior is where the whole kind of art of designing regularizers lies. Now, if you're trying to maximize this posterior, it turns out to correspond to minimization of a certain penalized energy, and you can identify the negative log of the probability density of your prior as the regularizer. And of course, the key question is how to choose the prior. Now, if you think that the way priors are chosen is that you really estimate the distribution of your data, then you're completely wrong, because that's impossible. If your data are images, if your objects are images in high-dimensional spaces, then this is not something that can be done. Okay, so typically what you do is you use simplifications. And Stefan this morning talked about microcanonical models and certain simplifications through a transform that simplifies in a way, Gaussianizes maybe partially the distribution of the data. Other examples are, Markov random fields. You have different simplifying models that, you use not because you believe that your data really follows this distribution, but because they're tractable, or you can do something with them in a way. Okay, so that's the caveat, right? Estimating P of X is crazy and it's not possible, and so you have to fix this. So what we do is we say, well, we will try to estimate, and this kind of goes, clearly to Stefan's talk, we'll try to estimate the prior in the space of certain moment feature transform. That could be, for example, the scattering transform. That could be the activations of a neural network. That could be something that's hand designed for your problem. Okay, and the question is now not, now we say, okay, there's some phi, but the question is now how to choose phi. And a hand-waving, like intuitive way to think about choosing phi is that there is this inherent trade-off. Okay, so you want to be able to estimate phi. You want to be able to estimate the density in this new space. So phi has to have some simplifying property, which we can call smoothing, linearization, Gaussianization, different ways to think about it. Okay, but at the same time, you want phi to be powerful. You want really to be able to regularize your inverse problems, even when they're real posed. So it has to have some expressive power. So these two requirements that are at odds with each other, and you have to somehow strike the right trade-off. What maybe you'd like to do is find an invertible Gaussianizing transform, but this is not possible. So one way to get partial Gaussianization is to use the scattering transform that Stefan talked about this morning, which uses averaging to smooth things, to simplify things, to Gaussianize things. But as soon as you start averaging, you lose invertibility. So if you average too much, you lose the expressivity of the expressiveness of your transform. Okay, so that's the trade-off that I'm talking about. Okay, so the idea is, you have some ugly distribution in the natural space of the data. You're trying to make it nice. Okay. Of course, there are some other properties that I'll just, quickly go over. So, you want to, if you want your representation to be stable to class preserving deformations, and you somehow want it to provide information that gamma doesn't give you. So if phi is only sensitive to low frequencies, and you're trying to do deblurring, then you're doing something wrong, right? So phi has to be incoherent with gamma. Okay? It has to somehow cut through the range of gamma and some other stuff that you're trying to recover. Okay, and so I will not, luckily for me, I'm always very, very scared when I have to talk about the scattering transform because I'm sure I'm saying many things wrong. Luckily today, Stefan gave the talk in the morning, so I don't have to embarrass myself. But basically, a good class of descriptors, are, for example, convolutional neural networks. But something that's kind of is better understood is this scattering transform. And just in a few words, again, for those of you who maybe haven't been here this morning, scattering transform is, the way it's constructed is that you have a wavelet transform together with rotations, and then you say, well, I'm going to look at norms of wavelet coefficients, okay? Either locally or over the whole image. If I'm looking at norms over the whole image, then I'm in this ergodic stationary processes regime that we heard about this morning. If I'm looking at things locally, then I actually maybe stand a chance to do something that's not ergodic. And then the important thing in the scattering transform is that you don't only look at the wavelet transform, you actually look at the interactions of the magnitude of wavelet coefficients. Okay? And the way you look at these interactions across scales and potential different positions in the image is to take another wavelet transform of each wavelet coefficient. Okay, and so, this actually models things that we know about. So you can intuitively feel that this may be a good description of your signal classes for solving inverse problems. Because, for example, if you take, so scattering transform uses complex wavelets. This is not a wavelet, but it's a wavelet. And so if you take this particular discrete filter, then you can recover the TV norm as the L1 norm of the convolution of your discrete signal with this wavelet, which is not really a wavelet. So in a sense, what scattering transform gives us, why it's good, is for all the reasons that Stefan mentioned this morning, it's locally translation invariant, and it's stable to deformations. But the way I like to think about it is that it's a signal class encoder. So it's encoding a signal class by sparsity, okay, by telling us what the sparsity of the class is. But not only at the scale of the pixels, but actually at many scales. And it also tells us how sparsity at different scales interacts. That's why it's powerful. Okay. So now let's suppose that our signals are ergodic, and we're really in this microcanonical world from this morning. And what I mean by ergodic is, the thing on the left-hand side for me will be ergodic, and the thing on the right-hand side will not. So this is a texture, and if I look at different patches of this texture, then they have similar statistics. Okay? And if I look at different patches of this brain slice, then they have very different statistics. Okay? So here I can recover something by averaging maybe spatially. On the right-hand side, I cannot recover anything by averaging spatially. Or maybe I can. I don't know. And of course, that's precisely now the statement in mathematical terms. If I average spatially, I can actually cover the sample average. And for scattering transform, if there is some mild concentration happening, then in fact the distribution of these features will be very concentrated. Okay? If you have images that are large enough, for example, then the distribution of your features will concentrate strongly around the mean. And the interpretation, again, I just have this on the slide, but Stefan gave a much nicer explanation, is that what you're doing is you're building a microcanonical maximum entropy model, and you just postulate. You say sufficient statistics of my signal class are specified by these generalized moments, which in this case are the scattering moments. Okay. In this case, well, as I say, because you have some concentration, then what you really kind of say is, well, the data in the scattering space is distributed around in a bump around this expected sufficient statistics. And one way to express this is to say, well, we have a Gaussian prior in the phi space. It's not really Gaussian because you'd have to multiply it by the Jacobian or something to really, if you really want to find the distribution of phi of x, it's not really Gaussian, but with sufficient smoothing and concentration, this is a very good approximation. It's not unjustified to say that we think that phi's are approximately Gaussian, and so we have this prior. Okay. So this prior is much simpler to estimate than the prior in the original space. And then this leads to the map estimator, okay, which is the usual thing, where what you're saying for this class of signals is that you want to regularize by requiring that the moments produced by your x are close to the expected moments, because you believe that those moments are being averaged over the image, and so because there's some concentration, they will actually lie in this small ball. This corresponds really to our framework from the slide 3 or slide 4 with the very simple estimator. So theta of y is just the constant, which is given by this expectation. And this is good for ergodic processes. We can estimate, of course, this from samples. And the main difference between full-on learning via convolutional neural networks and this kind of half handcrafted approach is that you can use very few training examples. So, for example, if you're trying to deblur textures, perhaps just a single example is enough. So here's an example. Here's a numerical, some numerical evidence of this. So I had another example of this texture, which I don't show on the slide. Okay, and then this is example number 2. I compute statistics from this example that I don't show on the slide, and then I blur it, and then using the proposed algorithm on the previous slide, minimizing the proposed loss, this is what you recover, and this is what Wiener filter gives you. Now, of course, there are more sophisticated baselines, but the point that I'm trying to make is that you can get a better SNR than Wiener filter, which is designed to optimize SNR without ever trying to optimize SNR. But at the same time, you get a sharper image. Okay, so that's somehow, which is not entirely obvious on this beamer, but yeah, it's true. You don't have to do deblurring. So you could say, okay, so there's another process, a simple one, I have to say, but a legitimate process, which is the Ising spin glass. There's the original. So you can take 24 projections. So you can basically compute like 24 slices of the Radon transform and try to invert from it. So if you use something that's off the shelf and that you shouldn't use in this case, but it's a good baseline, which is the filtered back projection algorithm, then this is what you get. And if you just try to make the generalized moments of the reconstruction be close to the generalized moments of the single training example I'm not showing you here, then this is what you get. And you'd be hard-pressed to find differences by naked eye. Of course, there are many differences, but it looks remarkably similar. Okay, that's just one training example, not a million. And again, this is for the simplest estimator from the data, which is just the empirical mean computed on one example. Okay, so what happens if you don't have this ergodic structure? Then okay, as I showed you on the slide with the norms, you somehow want to exploit the reduction of uncertainty from knowing the data y. Okay. And one way to do it is to talk about conditional ergodicity. So because you know that whatever you do should be localized with this feasible set, you could use, you could come up with this kind of conditional prior that tells you, well, I'll only work on the level set. I'll only work, I'll use the fact that I know that I have to be localized with a feasible set. I'm solving an inverse problem and I have some data. So let me try to use it already at this point. And, modeling this conditional probability, it cannot be more complicated than modeling the full prior, right? Because you're already localized. So potentially, this is a simpler problem. And we'll see that it indeed is in some examples. So this localization in this feasible set is what usually gives us the low frequencies, the large scale, which corresponds to the non-ergodic part, the large scale structures. And then, we could come up with something we call conditional map estimator, where instead of, again, so now there's this implicit conditionally Gaussian model, where instead of computing the mean, we compute the conditional mean, okay? So we replace the mean in the kind of the Gaussian model in the phi space with the conditional mean. And that's now our estimator. And this conditional mean can be computed, it precisely minimizes the conditional expectation of MSC, so the conditional MSC. And we can compute it again from training examples, because all of our training examples, so we suppose that we have some set of training examples. For example, xk and its blurred version yk, they all satisfy this property that xk is in script ay. So they're good training examples to minimize this. Okay, that's what we can do. Of course, the minimization, the way we search for this theta is within some class of estimators that we have to specify. Okay, so this is all great, but it seems that we are assuming that this wall in the phi space is circular and that we cannot extract any additional information from correlations between different features. And this is probably not true, because it's like we think that our transform is too good, its regularized is too much. And so what about the metric in this space? So to be able to talk about the metric, having this kind of adaptive prior, which depends on both x and y, seems to be an obstacle. Okay? And so it would be very nice if we could really have an ordinary map version of what we do. And so in the following, I'll try to simplify this framework. I'll try to tell you how we can model this using ordinary math. Okay? And to do that, I'll talk about something that's called a stable subspace, which is basically a subspace where I can get a stable reconstruction. So that's a finite dimensional subspace in which I can get a stable reconstruction of my object x from data y. I can get a stable projection in this subspace. An example in the case of blurred images is the space of all low-pass functions. Or, for example, the space of all piecewise linear functions on a predefined mesh. Okay? So usually you can get a stable projection into this subspace from the data y. Okay? So what we have is this stable subspace, which is specified by y, and it makes sense that we don't make our prior depend on the information contained in this stable subspace. The reason for that is that this would unnecessarily complicate the prior. The only thing that we actually want to estimate is the information that's orthogonal, that's in the orthogonal complement of the stable subspace, which is unstable. Okay. So this can be expressed by saying that our feature vector actually depends on the projection into the orthogonal complement of the stable subspace for some phi tilde. Now, if this distribution is simple, we can use the microcanonical model that I talked about in the beginning, but more often than not, for non-ergodic images like brains, this distribution will be complicated. It will be too complicated. And so the idea is to try and use a correlation between the projection in the stable subspace and the projection in the unstable subspace, or the orthogonal complement. Now, I like analogies, and the only way I can think actually is in terms of analogies, which probably irritates many people, but I'll give you an analogy of this that comes from speech coding, because my background is actually, in audio signal processing. And in speech coding, what you do is you're trying to code a stream of speech. So let's say you're trying to code marginally the sample xn. Okay? And so one way to do it is, what you have to come up with in coding is something called the Huffman code, which is the shortest, it has the shortest expected length of all the possible codes. So the way you come up with Huffman code is that you look at the probability mass functions that you estimate of your marginal sample, and then you try to construct this Huffman code. Unfortunately, if you look at the sample marginally, this is very complicated. First, it's complicated to estimate it, and potentially it has a large entropy. So the way you try to reduce the entropy is you look at something that's correlated with your current sample, and that's the past. Okay? So there, you have this past, you have past samples, and you build a linear predictor of XFN based on these past samples, and then you look at the prediction residual. Now, if you look at the distribution of this prediction residual or the dynamic range, variance, entropy, whatever you want, it's very small. It's much simpler to code, it's much simpler to estimate. Okay. And in this sense, okay, so what we're really trying to do is, we're trying to look at this unstable part as the current sample that we're trying to estimate, and the stable part as the correlated information from which we can extract something. And so we come up with these effective moments that are residuals. Okay, so that's the first part that only depends on unstable information. This is really what we want to characterize. But the way we're going to, simplify the distribution of this thing, which is potentially complicated, is by subtracting our prediction, our estimate of it, from the stable information. Now, of course, by definition of stable information, we can also compute this projection from Y directly, from the data directly. Okay? And now, if you use this fact that you can compute the projection of the stable state subspace from the data directly, you get precisely our estimator, because this theta tilde of phx is something that you actually can compute from Y. And so what we have here is, by the way, this only works on script AY, but we know that we are localized on script AY. Okay? And so what we have here is a characterization of our prior, which is purely defined on X. There's no Y anymore. Okay? And it's the same on the stable subspace. And now the question is this hypothesis that using this estimation we can do something good true for scattering coefficients? So here's a numerical example. So I plot scattering marginal, single scattering coefficients for the brain set. I just picked 3 at random. Okay? And so this is the distribution that you get. You can see that it's definitely not Gaussian. And because these are just marginal distributions, in fact, you can imagine that the product distribution, the joint distribution is something like a monster distribution. These are pairs of coefficients. It's still kind of bimodal, but you see that the third bump is already starting to form here, and potentially in high dimension of scattering coefficients, the actual distribution is not just 2 bumps, but many bumps. And so Gaussian approximation is bad. After linearly regressing those coefficients from the stable part, the distribution becomes, Laplacian. Not Gaussian, it's Laplacian. I'll pretend that it's Gaussian for the moment because it's easier to exploit correlations. But you can see that the level sets, even of pairs of coefficients, are squares. So this is really jointly Laplacian, which is very interesting. And I don't know if this is completely anecdotal and random, or there's something there, because I probably got this image like yesterday or the day before. But in speech coding, residuals, it's like the classical Huffman codes are designed for Laplacian distributions because they actually know that their residuals are distributed as Laplacians. So that's somehow maybe completely random, but maybe interesting. Okay, so one question is the following. Like, if you have a lot of data, why don't you regress X directly? If you have a certain measure of loss, maybe you want to regress this measure of loss instead of regressing something in the space of some feature transform, which seems like a roundabout way, because eventually you want to get at X. Okay? So maybe we can think about the properties of the feature transform that will help us stay close in terms of some predefined metric, like, for example, the MSC. So just suppose that your feature transform, whatever it is, activations of a neural network, scattering transform, whatever you take, your moments obey a certain, they're roughly an Euclidean embedding. But you don't want this to be the case over the whole space. You only want it to be the case on script Y, script AY. Okay? So only on the space of visible signals, your moment transform is computing an Euclidean embedding. And then we can define 2 estimators. So now I can look, instead of looking at map estimators, we can look at estimators that minimize certain MSCs. We can look at the MMSC estimator, which minimizes, the MSC. If, for example, that's your metric of choice, that minimizes the MSC in the signal domain. And we can also look at the estimator, which I'll call here X hat flat, which minimizes, which is our estimator, which conditionally minimizes the MSC in the scattering space. That's something that, that's the metric that you're trying to optimize. Okay? And conditionally meaning that you're looking at all estimators that produce something that's consistent with your data. Then it turns out that the MSC of our estimator is upper bounded by this, sort of frame-like bounds, B and A, times the original MSC plus some variance that's a property of our estimator. Okay? This is an opportunity to remember the fundamental theorem of machine learning that we heard about yesterday from John, you know, and that originally comes apparently from Ben Hecht, I mean, the name for it, is that this variance is sum of two terms. It's the bias of our family of regressors that we choose, and finite sample variance, the fact that we're estimating our estimator from training examples, okay? And that's this fundamental trade-off that we have. The fundamental trade-off is that if you have only a few training examples, then it makes sense to handcraft features, okay? Because you can optimize this trade-off. If you have one training example, then convolutional neural networks will operate on a horrible point in terms of this trade-off, right? And we can operate at a better point. Because maybe we can, you know, we will increase the bias because we have a restricted model, but our variance will be much smaller. Okay, so that's kind of the rationale. One other way to think about it directly in the space of inverse problems is that we can define different estimators of our moments. So one estimator is the empirical. That's what we really compute. So that's what I've shown you already. So over some family of estimators, feature estimators, script M, we minimize the empirical loss. But what we really like to do, what we would want to do, is to minimize the expected loss. Unfortunately, you know, we only have a finite number of training samples, so that's the first line is what we can do. And we can try to compare this to an MMSE estimate of our features. Okay, so let me just go quickly here because I'm running out of time. But what you can see is that the NSE suboptimality of your estimator is then approximately given precisely as the estimation or finite sample error, the difference between like minimizing the expected loss and the empirical loss, and then by something that's easily interpreted as the model error of your representation, which is not surprising, but it's really casting this fundamental theorem of machine learning in the context of inverse problems. Okay, and so let me see. Okay, so there's a few, so let me just show you to wrap up with a few numerical examples. So in these numerical examples, I choose the class of estimators to be affine estimators in the feature space. So the way I'll do it is I'll say, okay, so I have some data Y, I'll apply some right inverse, or even just an adjoint to bring it back to the image space. Then I'll apply the scattering transform to it. And then I'll try to regress using a linear or affine estimator. I'll try to regress the features of the sharp image or of the original from these features that are just, you know, right inverse and then the feature transform. Okay, and so here's an example with deblurring. Again, it's not the state-of-the-art deblurring algorithm, and but you have to know that like this is, you know, the training here is done on hundreds of samples. Okay, so it's not like millions, and you can see that it beats the Wiener filter, which is, you know, optimized over a certain restricted class to minimize the MSE. Okay, you can't really see that this is sharper, but you have to trust me. So it works for a variety of things. That's a power also. So you can plug it in denoising. Again, Wiener filter that's designed to optimize the MSE does worse, perhaps at the expense of the large background, but even if you cut a portion, this is still a little better. You can apply it to tomography, so you know it does much better than filter back projection. If you have tons of training examples, then you should do what Mike McCann is doing. I mean, you should really not use this. But if you have only a few training examples, then this is perhaps a good strategy. Okay, and you can do something that when you train a neural network, you cannot do, and that's you can vary the amount of regularization. Imagine that you're a clinician. It's like, and you want to interpret different images. And so you have this neural network which outputs a single image. Of course, you can train it to output many images, but maybe you'd like to, you know, see what the image, you know, what does a lightly regularized image look like versus what a heavily regularized image looks like. And so you can vary the, you know, maybe you can say, okay, that's under-regularized, then maybe this is the sharpest that we can get, and then maybe, you know, this is too much, and, you know, there's a bunch of artifacts, okay? So you can kind of create a movie for someone who's looking at these images that they can interpret the way they want. Okay, so let me just quickly rev up. This is powerful models for, you know, ergodic stationary processes, but we can adapt them to also work with real signals, and it's kind of a cute way to expose fundamental learning trade-offs in the context of inverse problems. So if you just have a set of features that you believe are important for your class of signals, then this is one way you can use these features to regularize using referrals. Okay, and